So next we're going to talk about glulam beams, and we're going to go through basically the same process we did for sawn lumber, but now we're using a different beams with different properties in a different chapter of the code. So glulams are basically laminated wood beams. The way they deal with the process here is look for a certain lumber grade, figure out what kind of joints between the different laminations, because we're going to want to make most of these beams longer than a single board length, because one of the benefits of laminate is to have a length and kind of cross section that's not available naturally, or that would be very expensive or tough to find naturally. So one of the reasons is we want a size not available naturally. So now I can get much longer spans and much bigger sections as needed. Decide what kind of joints, because like I said, we're not just going to have the length of limit by the length of individual boards. And so, if I've got different laminate layers here, is there, how are we doing the joints? Adhesives that go between the layers, and those are based on the expected moisture in the wood. And like I said, for size, the other thing is nice about laminate is I can do different shapes. And I'll show you some pictures here on the next couple of slides. And I can put together these kind of laminate sandwiches to improve the overall quality of the beam. So I can use the highest quality of wood on the edges where I have the highest stress, and a lower grade towards the center. So I can use those things together to get an overall high quality beam when I may not have been able to do that as individual boards. So in other words, we're customizing this a little bit. Okay, so some examples. Here's a glulams are pretty popular when you have to have a decent span in a house or a commercial building. You may find quite a few residences that have these in. This is pretty common at this point. Here's in shipbuilding. So you see, sorry, not shipbuilding, but in shipbuilding it would look similar to this. This one's in a church, but it's got the kind of curves you'd see in a ship, or if you're just looking at curved beams for a ceiling or whatever. It's a neat architectural feature. In addition, we do have wood trusses, curved wood trusses in this case, on a bridge. So some of this is aesthetic, some of it is, the right structural shape, since I have the ability to do some different shapes with laminates. Here's another example of a curved structure, and you can see where it's spliced together up here. So you've got really unique laminated beams in this one. Actually, frames for that matter, beam and column together. There's an up close. Lots of laminate layers in this particular one. Very impressive. All right. So let's talk about the code pieces of this. Just a quick overview before we go through some examples. The glue laminated beams or structural glued laminated timber are in Chapter 5 of the NDS code. Okay, so they follow the same format as we just did for sawn lumber, but it's in Chapter 5 instead of Chapter 4. So there's a section that talks about, what to look out for in general. There's the reference design values that we're used to using in tables 5A through 5D in this case. The adjustment factors, so those are your C's, and then special design considerations. You still, the general design for beam, shear, and deflection is Chapter 3. So this is Chapter 5 is just specific to the property and design value and considerations specific to glulams. So general notes, here's a good picture of two here. So it's not little thin layers, they're actual boards that are laminated. They say thin laminations, but they're thin relative to the cross-section size, but you shouldn't think of them as little bitty slices like you see in plywood or something like that. They're glued together, end jointed, They may have some different types of joints depending on the length. They can be, practically any size or any length, and the cost will depend on that size, length, and shape. Individual lambs, in other words, these boards are typically 1 3/8 if they're southern pine, and then for some of the western species, they may be closer to 1.5 inch or at 1.5 inch. The members typically have widths from 2.5 to, getting close to 11 inches, but you can, as you saw in the pictures before, can do much larger ones than that, but these would be more standard. And in fact, because they're used pretty widely in light commercial and in residential structures, there's stock sizes of glulam beams, and that's why we can go into the tables and look at some of these properties. So these are some of the stock sizes. Layups. So the layups is how you put the different boards together or the different lambs together. They can be all the same, but what would be more common would be to utilize the wood most effectively would be have the strongest ones on the top and bottom. So the lambs or if I'm looking at a cross section here, if this is a simply supported beam, right? On the bottom side, we've got tension. On the top, we have the biggest compression. So if you think of your bending stresses, right, top and bottom are my extreme fibers. And so that's where I need the best properties of my wood. And as I get to the neutral axis, where in bending there's zero stress at one point, but very low stress here in the middle, I don't need that high quality of lumber. So the location of maximum tension is where they put the higher quality lumber. This makes these types of beams efficient and cheaper instead of just putting, smashing together a bunch of high top quality structural lumber. A balanced beam will have the same lumber on top and bottom so that you have the same basically I value. So if you think about my glulam beam here, if I had one you can think of as strength, but one type of board on the top and a different one here on the bottom, then the S value or the I value will be different. But if I keep it balanced, top and bottom, in other words, symmetrical about the axis I'm looking at, then I'll have the same S value. We would use this type of glulam in cantilevers or continuous beams. So a continuous beam is going to be switching back and forth from tension to compression. Okay, cantilever beam is, if it's just a basic cantilever beam with load on top, it's going to actually be tension top, compression bottom, but don't want anybody to pull a Frank Lloyd Wright type thing and have it flip the wrong way. So I suspect that the cantilever piece is one of two things. A lot of these cantilevers will be part of a continuous beam structure, or if it's a pure cantilever, we want to reduce error in the field that these get placed the wrong way. Now, if I have a simply supported beam, I can actually use an unbalanced beam because, the compression and tension requirements that I need are different. So I could actually just have, in my laminates here, something different on the top than I have on the bottom on the tension side. So it's kind of custom designed in that way. If you've had the pre-stress class, it's not so different in concept than what we do there as far as where we put strand. If you have a unbalanced beam, in other words, one that's got a non-symmetrical here about X, you need to make sure, so the highest grade lumber is going to be on the tension side, need to make sure it's on the bottom for these simply supported beams. So for simply supported beams, if I have this, the beam needs to be oriented so the bottom is the correct orientation, and that's where the highest grade lumber is on the tension side. Okay. Glulam reference design values. Let me just catch up here on my notes. Okay. They're specified, the glulam bending members are specified. similar to what we've done for sawn lumber, maximum allowable bending stresses, is it visual or mechanically graded? And then the new piece for glulam is what is the specific combination of wood species, and because I'm combining those and then combining different grades of or different properties of lumber maybe throughout the section, I need to have some of the information provided in that designator. So for example, if I have a glulam, it might be a 24 FV4. What that means is the 24F it means that it is 2400 psi flexural stress, so allowable. So this would be allowable bending or flexural stress of 2400 psi. So I know by this designator what my allowable bending stress is. And the V4, as you might guess, has something to do with shear. In this case, it's going to indicate, yes, the shear allowable stress, but it's also going to indicate the modulus of elasticity number and other characteristics. And it also means that it's visually graded. If it has, so the V is actually doesn't mean shear, but it does. If you have a designator of E instead of V, that's going to mean that it's mechanically graded. Visually graded would be mechanically graded if it's an E. So you're not totally wrong if you say this is flexure and this is shear, but there's more to this than just shear. We're looking at the shear stress, but we also are looking at the modulus elasticity, and actually the V means visually graded. You're going to get an E if it's mechanically graded. All right, so, oops. Just like in saw lumber, so table 4A, 4B, 4C, etc. I'm going to be in the 5s. So table 5A has all the reference values, mostly bending stuff, and softwood beams. Hard or softwood axial tension and compression is in 5B, and then table 5C is where you have your hardwood glulam beams. Oops, I need to shrink down here a little bit. And table 5D is the axial. So A and B are softwood, C and D are hardwood for flexure, and then actual tension and compression. And this just lists the values that we'll find in here. You will see a little bit of difference in the tables where you've got F sub Bx and F sub Bx, so plus and minus if they're unbalanced, so positive and negative, or top and bottom basically. On page 64 and 65, when you're in this area, you'll see shaded rows that are mechanically graded and unshaded rows that are visually graded. All the footnotes in these tables point you in the right direction. So when you go into a table, I'm talking you through some of this, but when you go into these tables, no matter what code you're in, but particularly in the wood code, read all the little footnotes first and make sure you understand the different pieces. So shading means something, it may have a superscript on it and things like that. So you want to check and make sure that you're interpreting the table correctly. Okay, so and we're going to do examples so you can check through this. Okay, one thing that if you've had the steel class or the pre-stress class, we've talked about camber. In other words, if I have a beam like this and I load it up, it's going to have some deflection. If that load is just my self-weight, right, it's still going to have a little deflection from self-weight. So ideally, when I go put it in the field, instead of starting with that little deflection from self-weight, we're going to camber it or design it with a little arch to it, or a little upward deflection, so that when I place it in the field and it's under supporting its own self-weight, it's flat, or even better yet, still has a little camber so that when I add on the other permanent dead load, I'm close to level. Okay, This allows me, in a case where deflection is going to be important, to meet deflection limits. So you remember the last sawn lumber beam we just did as a design example. I got through everything, and then the darn total load was the kicker. It didn't meet the deflection constraints. So if I had the ability to camber, which I do in the glue lams, but not really in the sawn lumber, in the glue limbs, if I can camber that a little bit, I start out with one of the issues here. And what we were doing with the sawn lumber are not super long spans. The glue lambs now, because we can do longer spans, deflection is a big issue. Okay, so it's very different than concrete because concrete's a heavy kind of stiff material. Steel and wood are more more often, they're more flexible material. They're more often controlled by deflection or sway if you're looking in the other direction. And so by building in this camber, I'm able to customize and get more efficiency out of a section. So we talk about camber and prestress, we talk about camber and steel. This is more the case of kind of what we're used to dealing with in steel, so that we make sure that deflection doesn't control so much so that I have to go up too much in section size to meet just the deflection requirements. Okay, so glue lambs can be bent in the opposite direction in the shop as they're mocked up and laminated. And they recommend, if you have a roof beam, you should camber it 1.5 times the calculated dead load. So this is a full dead load deflection. Floor beams calculated for 1 times the calculated deflection. Why roof and floor being different? Well, we're standing on the floor and the roof is a little farther away from us. It's not visually or walking around on a floor that's cambered. You'd notice more quickly than looking up at a roof beam that's cambered. Curved bending members. Okay, this is a different type of curve. So if this is curved in the other direction, the amount of curvature added for typical cambering doesn't create a situation that's a problem, but then we can also have curves in the other directions. But if we're talking about the curves in 5.4.1, we're usually not going to have a situation where we have an issue with that radial tension. Okay, so curvature for typical cambering is not an issue, but if I'm using curvature in another direction or for another reason, that may be a little bit different. Okay, and we'll talk about that as we go through the calculations. Wood ignites at about 450 Fahrenheit. So fire performance, we know wood burns, and that's an issue. We can start seeing charring as low as 200 Fahrenheit, and it'll char at, this is kind of an estimate figure, but a 1/40th of an inch per minute. So 30 minutes of fire exposure, you basically would have the outer 3/4 inches would be damaged charred wood. So what we're trying to say here is that when we have a very large section size, you may have charring on the outside, but it may still be structurally sound or safe. Okay, so it depends on how long the intensity of the fire and the fire exposure time. The adhesives are designed so that they don't burn at a faster rate than the wood, so they don't really change the performance of the wood. And the char, once it's formed, will insulate the interior part of the member. And so it burns at a slower rate after it's charred on the outside. So the fire codes will tell you the minimum size glue lamb that you need to have for 1 hour fire rating, 2 hour fire rating, etc. I'm not going to be covering this in this class, but it's just kind of a note. You all know I favor concrete quite a bit because that's what I work in, but wood definitely is used widely in light commercial and residential and is the right material up to a point for that. And it's definitely cost effective. And so, I want to just point out that just because it's wood doesn't mean it's terrible in a fire. It can still have a certain fire rating. I think it's just as you look at the intensity and the duration and the amount of fire that you're seeing in an area, that It could be okay, but you may have to move to a different material if that's a real concern. Moisture. So glulam beams, they'll typically be around 12%, but you have to have, instead of a moisture content, we were using 19% for sawn lumber, you now have to be below 16% for using for the glulams. You have less shrinkage problem than the sawn lumber, and so you also have less checking. Okay, but the checks that you get are near the glue lines because that's, so if you look from the side, get checking near glue lines because you have a differential in drying between those different material or those different boards. So you definitely can have it occur, but there's less of an issue. Okay, so resources for glulam. If you go on apawood.org, you can find a number of resources for designing with glulam, dealing with connections, what kind of products are produced typically in glulam, common designations that we'll see in Duluth for interior use are Southern Pine, 24F, V4, and V8. The V8s are typically continuous or cantilever. This is a real typical section for other uses, so simply supported beams essentially. So these are what we're most likely to see here, and therefore you're going to see those in some of our examples. Okay, so how do we handle, I'm going to keep going here. I know this video is going to be a little bit longer, but just an overview. This is similar or almost the same as in sawn lumber. We're just going to be using different numbers because we're going to use the information from chapter 5 and tables 5A through D. So just like before, we've got our little f sub b must be less than f prime b. So our demand, you find it the same way you did for sawn lumber. Our f sub b prime is the same way we did for sawn lumber. You will go into a different table to figure out what your C values are and which ones you use. Otherwise, it's the same process. If you have a simply supported beam where we're looking at different top and bottom stresses, so F sub B plus is bottom stressed and tension or positive bending. F sub B minus is top stressed and tension or negative bending. Okay, so positive bending, which is our simply supported beam that we're used to seeing under gravity type loading. Adjustment factors, we've got load duration, wet, service factor, temperature, beam stability, volume factor. There is a footnote under the table. So table 5.3.1 is similar to the one in chapter 4 we've been using. Under there's a footnote that says the CL shall not apply simultaneously with CV. Use the lesser of the two. So the volume factor and the stability factor. And so I've got a couple notes here that you'll have in your notes, but one thing is you have to have less than 16% instead of 19% for glulams instead of sawn lumber. Most other stuff is the same. Some of the rule of thumb methods that were in chapter 4 stuff is specific to sawn lumber, and so you get a little bit different version here in the glulam section. So you can go in, take a look at chapter 5, read through that, take careful or look carefully at the tables and some of the footnotes. Other adjustment factors, same flat use factor, curvature factor. That's what we're talking about when we're doing the curved beams. Stress interaction factor. This is for tapered members. All right, we're going to keep these fairly straightforward. Excuse me. Shear, same. Depends on hardwood or softwood where you go in the tables. Shear parallel to the grain or perpendicular to the grain. Strong axis, weak axis. In this case, instead of saying shear parallel or perpendicular to grain, this is looking at which direction the laminates are. Right? So is it loaded this way or this way? Adjustment factors, shear, CD, CM, CT, the temperature one, C sub VR, shear reduction factor. So this is some special considerations. Non-prismatic, that wasn't an issue in sawn lumber, but it can be for glulam. Connections, notches, and if we have an impact or a cyclic type loading. Deflection, same deal, same way of doing this. One item, and you may have noticed this when you were looking in these tables, some of the tables before, there's different E values. When we're doing deflection calculations, we do E sub APP. We use E true when we're looking at some specific cases where we have a super short, deep beam, and I'm looking at deflections because of shear. So this is typically what we're using. And if I have a column stability issue, that's when I use E minimum. So we've been using this E sub APP. All right, so next up is an example, and I will do that as a separate video.